Hello everyone, I will present meta-learning for multi-label feature classification. So as an introduction, we want to differentiate between multi-label classification and standard feature classification compared to the multi-label feature classification that we have in this paper. So in multi-label classification, you are given one image with multiple objects and you want to discriminate these two objects with the other classes. So for instance, this prediction has a high scores for apple and also dog. But in standard feature classification, you have a support set that contains banana and also apple. And you also have a query image, which is banana here, and you want to compare and calculate the distance, for instance. And you will get this high similarity score between banana in the support set and also in the query image, but low similarity in comparison to the apple. But in multi-label feature classification, you are given a support set and also a query set, for instance, with multiple objects under one image, and you want to compare them. So for instance here, it has high similarity between query and also the support set for apple and also orange. So for instance here in query set, we want to predict the labels based on the support set. So we want, so there might be like multiple objects and classes here in one image, but we want to restrict the number of classes to be the same like in the number of classes in the support set. So for instance, we have stop sign as the reference and also car and also bus. So we only apply labeling for these three classes. And for our method, we adopt different strategies from single label feature classification. For instance, we apply prototypical network under multi-label settings. Here we use prototypes for each class, and then we calculate the distance between the prototype and also the query embeddings. And here we have the loss function, and y is the ground truth with the normalized version here. So it is not a one-hot factor. And we have also the softmax function with respect to the negative distance here. For relation network, we have a relation module here that compares between query embedding and also the prototypes. And here we apply binary cross entropy because this relation module will produce 1 or 0 in the end. For multi-label propagation network, we create the graph that contains similarity between instances in our support set. And also we calculate the label propagation here. And we apply mean squared error between the real label and also the prediction that we have through label propagation. In addition, we also apply neural label count that can count how many objects inside an image. So we have this module phi. So this module will compare between the embeddings from the support set and also from the query. And we have this z as the context, which just average all of the embeddings in our support set. And label count objective, we calculate basically the entropy of our prediction for counting the objects inside one image. And in inference, we calculate the label estimation and also labels in the support set that we know how many labels are objects in the image, and we do voting. For instance, here with histogram, we take the highest vote as the inference to define how many label inside this query image. And we show the results on MS-COCO, OpenMake, and also iMaterialist. As you can see that we can beat lasso as the state-of-the-art for multi-label feature classification. And also we apply for OpenMake that we can see the comparison between prototypical networks, relation networks, and also label propagation network. So this is neural label count performance in 10-way and also 15-way, also with base classes and novel classes. So we have also an ablation study that showed the impact of SHOT on MS-COCO for label counting and MAP. So in conclusion, we have measured the performance on 3 challenging datasets, MS-COCO, iMaterialist, and also OpenMake. And we introduced a meta-learning framework for multi-label feature classification and a label counting module. Apart from multi-label feature learning protocols, we have proposed a neural label count module to estimate the number of labels. This is built based on the voting system to handle weak predictions.